Yeah, thanks for the kind introduction. Hello, everybody. Um, yeah, let me first begin on how we came to 3D printed sensors. So my colleague Frieda, he's working on 3D printed devices in our institute. He's focusing on 3D phononic crystals, so acoustic things. Furthermore, he's focusing on microfluidic filters, which were built in with a few microns here. It's built with a nanoscribe. He's furthermore focusing on gas chromatography columns, which you can slightly see here. And of course, he's focusing on microfluidic systems to build connectors and for packaging. So he's not working that much on sending structures itself. But I'm working actually on sending structures. So my focus is printed sensors for material integrated sensing. For example, a printed strain gauge on a partially isolated carbon weave. I'm going to present this as a poster tomorrow. And you see the actual strain gauge is integrated in the CFRP beam. Furthermore, I'm focusing on building sensorial workpieces to characterize manufacturing processes. These are printed thermopiles or thermocouples, and this workpiece is then cutted to characterize the temperature which is going into the workpiece. Another thing, what I'm doing is printed strain gauges for integration in aluminum during high pressure die casting, and these are printed strain gauges here, which are then integrated during the casting process. So yeah, and since we are working together, we were discussing about what can we do with, or how can we build up printed sensors, and we thought, yeah, let's merge our additive additive manufacturing technologies, and I think that's what many people are doing here. Yeah, it's like a vision what a lot of people, like the first presenter Simon has. It's to build up 3D printed devices, 3D printed sending parts. And so, yeah, we had this idea of a pressure sensor to build a fully printed pressure sensor. Let me first talk about the mechanical part of the sensor. So this is the actual pressure chamber. It's a circular cylindrical cavity. We have integrated fluidic connector ports for the tubing, for the connection. The cavity height is 800 microns, and the membrane thickness varies between 100 and 500 microns, so the sensor thickness itself is between 1 millimeter and 1.8 millimeters. We have a solid contact pad area here for the electrical connection. We have symmetrical design for both, for the front and the back side resistors, which will come back later to it. So yeah, the design is symmetrical, and the orientation is vertical during printing, so that we get coplanar front and back membrane. So we have actually two membranes. The design of the electrical part is yeah, very basic. We have two strain gauges, that one in the middle, which is sensitive to the tensile strain, and we have one close to the edge, which is sensitive to compressive strain. You can also see the diameter of the chamber, which is 18 millimeters. The width of the strain gauge track is 150 microns, and the electrical path here is 750 microns. We made everything in a half bridge layout. You can see it here. One is set under tensile strain and one under compressive stress, and then we can monitor the bridge voltage. And of course, due to the fact that we have two membranes on the front and the back side, we can also, it would be possible to have a full bridge design. The advantage of this design is that we have only one printing step. The disadvantage is, of course, that we have relatively high lead resistance in comparison to the actual strain gauge. And the final electrical connection is done here by wire. So that's the design. So let me come to the fabrication process, the 3D printer. We have a per factory micro high-res printer. It's a micro stereolithography, which was told by Simon in the morning, in the first presentation. So yeah, it's a lamp, and then with micro mirrors, it gets actually exposed, and the devices build it up. So it's a DLP machine with a resolution of 31 microns in plane, and 25 microns per slice. So the 100 micrometer membrane, that's only 4 layers, and yeah, that was a little bit tricky. We took high temperature with the resin, HTM 140, which is necessary because for the curing process of the actual sensor, it should be high temperature resin. Yeah, there are a few challenges. We need precise exposure settings to avoid gelation inside the cavity, because yeah, finally there is the unexposed material in it, which has to be rinsed out of the system. So we need thorough rinsing of the cavity to remove all the resin. And of course, we should be careful with it, with a membrane, especially when we have a very thin membrane. Yeah, the fabrication of the sanding structure was done by a low-cost manual screen printing. We have very low cost for €5. It's a very low-cost mesh. We used standard ink from DuPont. It's a stretchable conductor. It cures at 120 degrees Celsius before we let it 10 minutes for leveling. Yeah, as I told before, the contact pad was done by copper wires, and we use electrical conductive epoxy, which was also cured at 120 degrees. And you see our final device is set up here. I also brought this sensor, so whoever is interested in the device, feel free to contact me during the lunch or after my presentation. Yeah, and then of course we did the characterization on the sensor. So we set up a full whetstone bridge with 2 adjustable resistor decades. We used a pressure controller to set the pressure with a supply voltage of 1 volt, and we recorded the bridge voltage with a multimeter. And you can see the results for 2 different sensors. This is the membrane thickness of 300 microns. And you see as soon as the pressure increases, there is a change in the resistance. And of course, we do not have linear response here due to the design. We get nonlinearity. The thicker the membrane, of course, the relative resistance changes less in compared to the pressure, which we also expect because a thicker membrane is more rigid. And it looked pretty smooth. We weren't expecting that it looked very nice. We thought it's more like, yeah, not that smooth. We also did a characterization on the sensor surface, which is actually very important because we need a relatively smooth surface for the printing process. If we have deep trenches, there might be a risk of a membrane burst, of course. So the surface roughness was very low, with average roughness less than a micron. Another fact is that if we also checked the printed line, which is here red. So the height of the printed line is only 3 microns, and thus it's less than the membrane thickness, and so it does not influence the sender signal. So if we have really huge or thick printed lines, that would influence the sender signal. Yeah, let me come to the conclusion. So we showed an idea of combining different additive technologies with microstereolithography and screen printing. The thing we showed was like a proof of concept for a 3D printed pressure sensor. And we got a well-defined sensor response to pressure changes. Of course, that was just a first sensor we produced. Further investigations have to be made on two-step screen printing maybe, so to reduce the conductive leads. and to use a resistive paste for the strain gauges. We definitely need a sealing for the sensor structures due to the oxidization of silver. You will see it if you see the sensor, it's already oxidized. It would be better to not use the screen printing process, but inkjet printing. You are more flexible in designs. It's easier to adapt it. You get faster production. And of course, we want to focus on other sensors like vibration sensor or flow sensors, what Simon also said in the morning. Or maybe you guys have idea which sensor you would like to print. So yeah, thanks for your attention.